morning, ladies and gentlemen. It's always scary to give a talk after someone like Nick. And in a way to look at my talk now is to give a more theoretical interpretation of what just Nick said. That's the way to look at my talk at this point. Another thing to say is, if you see my title and understand the wording, then you has already understood what I'm going to say. So there are three keywords, MJO, and then asymptotic non-divergence, and nonlinear wave. And there's a question mark. So goal of this talk is to remove this question mark from the mind of all the audience in this room. And I called it review because I borrow many biographics results from other people, but I believe statement given here is original enough for most of you. Now, before going, I have to thank three people, particularly Chi Dong-zan, Samson Hagos, and Chris Holloway for many discussions. But I have to remark, they may not agree with what I'm going to say. Now, of course, we should start with MJO. Probably all of you know what it is, but it's just quick review. These are schematics provided by original authors, Matt and Julian. This is not so visible, I realize, but it's essentially eastward propagating large-scale circulation, associated convection generated over Indian Ocean, and as convection moves eastward with time, associated with this large-scale circulation, and convection dies out around Central Pacific deadline, but dry component go around the globe, taking about 30 to 60 days. So summary is it's 30 to 60 period eastward propagating. Of course, it's atmospheric, and often we consider equatorial wave, kind of equatorial wave. And of course, key question is what is mechanism? And the way I like to address this question as a starting point is to see how global models are doing. And my pick is the one by Chris Holloway using a UK unified model. And this is a kind of summary of their results. Top left, this is their simulation domain, kind of half globe over Indian Ocean to half Pacific. And so this is longitude time section. From trim observation, we see nice MJO structure moving eastward. And there are 6 cases they considered. They are detailed, different resolution, and with or without parameterization. But quick point I like to make is none of them simulating this nice eastward propagation observed. Not quite. Now, look at same thing with slightly different variable. Bottom is observation. Now this longitude height section of vertical velocity, or more precisely pressure velocity, over 7-day period. This is earlier phase and towards the end of simulation. And bottom line is, actually I realize it's not that bad, but the simulation tends to be too noisy or not noisy enough compared to observations. And to compare with this zonal wind prediction, this, to my eye, much more consistent with observation. So in this simulation, and with many other simulations, more than often, this large-scale horizontal component is pretty much well simulated compared to convection-related variable. Another simulation by Monnier et al. Using MM5 makes same point here. Top is observations, and bottom is the simulation. Now this is frequency wave number spectrum for zonal wind 800 for left side, and OLR to right side. And point is, this zonal wind 850 is pretty well, except for eastward propagating mode is a little bit too weak, but never mind, it's not so bad. And you may say same with OLR, except we have to look at this red box that is actually amplified by factor 3. So OLR convection response is too far weak in this simulation. So again, it's getting a point. Dynamical part is pretty well done, but convection response is not so good. So this is a summary. The difficulty is in splitting convection precipitation, but more often we do large-scale circulation associated with MJO pretty well. These are just two examples, but if you go through recent literature, it's pointed to the same conclusion. So that's a summary. Dynamic component MJO can be well simulated without convection, and boil this down is we may think of something like dry MJO. And kind of impression behind is convection within model is kind of working like a damping than helping MJO. Now, so why we can think of dry MJO something closely associated with convection? The notion to introduce is what I call asymptotic non-divergence. And the way to demonstrate it is simply make a scatter plot of vorticity against divergence over 3 vertical levels taken from two-core large-scale array data set. And what you see is this scattering is always horizontal than vertical. That means vorticity is always dominant than divergence over this large scale. So that's the idea of asymptotic non-divergence. Of course, this is kind of gross statistics, but I realize for many people it's better to call it quasi-non-divergence in analogy with quasi-geostrophy. But point is, in leading order, we just have to consider rotational component, and dynamic is vortex dominant. And of course, because it's non-divergent, there's no convection to leading order. So we can consider MJO as dry dynamics to leading order. Can we? Of course, this was more general. So can we say the same specific MJO as well? I found a very nice paper by Adams et al. Just appeared this year. They did very careful analysis of decomposing wind field associated MJO into divergent and rotational wind field, and composite over 8 phases of MJO. And in my crude eye, rotational wind field spread more globally than divergent wind field. And it's equally significant, and it seems to me it's more dominant with rotational wind, which is debatable, but that's kind of argument here to support the idea. Now, so if we think MJO is asymptotically non-divergent, then we can consider of dry wave dynamics. So how can we move ahead along this perspective? And there are 2 options. Well, look at wave dynamics, and there are only 2 slow equator waves we can consider here. These are 2. Number 1 is Kelvin wave, and this is not so good. Well, it's eastward propagating, but that is good news, but it's still too fast. And worse than that, it's non-dispersive. Phase velocity fixed, so we can't change it. Rossby, so we have to cross it out, unfortunately. But Rossby-wave has a nice future. This depends on wave number. So there's a possibility we can tune this up. So that's the idea, or the thing to look at. This is my key slide. So we look at linear Rossby-wave dispersion. This is a way to summarize it. I introduce scale parameter LP square. The phase velocity is equal to minus beta LP square. LP square inverse equal to zonal wave number square, longitudinal wave number square, and inverse square of deformation radius. And things to remember is, MJO is for propagating, and beta parameter is about these values. So first thing to realize is, because this is eastward propagating, this is positive, so LP square must be negative. And actual number is something like 1,000 kilometers, but imaginary. That means if we want to understand MJO by linear Rossby-wave dynamics, it must be evanescent or exponentially decaying wave. Is it clear for everyone? It's kind of trivial and even stupid, but this is very important point to understand everything. How many minutes I got? Oh, gee. I think I have to run a little bit. Many people say this is just laterally force, and this is an example to show if you put lateral forcing, we get this eastward propagating zone of wind much better than otherwise. But then, what does it mean? So we go back to this linear Rossby-wave dynamics and put reasonable ordinal wave number. And what it means is this latitudinal wave number inverse must be again imaginary and 1,000 kilometers. So even you force laterally at whatever latitude, this signal should die out with 1,000 kilometer scale. So you wouldn't see anything in linear sense by lateral forcing. So it must be something nonlinear. We need kind of nonlinear resonance. Now, nonlinear problem. It's nice to consider this is solitary wave, solitary nonlinear. So you got very high amplitude at MJO center, but you get long tail. So it's exponential tails. And beauty of this theory is tail is linear, and if you're only interested with propagation, we just have to stick to this tail part linear. Then we just have to put this typical latitudinal scale and do the same thing in longitudinal direction. Then answer is it's tail decaying with 1,000 kilometers, and that should explain MJO. And this is a nice simulation done by quite a few years already. Niels Wedi and Piotr Smolarkiewicz. Left frame is snapshot, and this is time longitude section. I think I have to wrap up.
You can keep going. You have several minutes. Go ahead.
Yeah, well, this is my last slide anyway. The way to wrap up is look at history of mid-latitude synoptic storm problem. And good old days, this is more or less British history, but they're worldwide influenced by Sir John Mason. He strongly consisted synoptic storm problem is essentially problem of rain formation. And very nice textbook to look at is by Francis Lutlam, written around 80s. And this is a very good textbook, I believe, except for if you look at Synoptic Dynamics chapter, there is no reference to ED or Charney. And that's where we're standing now with modern generalization. We tend to believe this is driven by convection and tend to forget this nonlinear wave dynamics, which is crucial to the same extent as paraclinic instabilities are important for understanding synoptic storms. And that's where I should put red mark, and I think I can stop. If everyone convinced, then I'm happy. Otherwise, I will get questions.